Niels Bohr then used Einstein's concept of light as quantized photons, and of course Newton, centuries earlier, had said that light was a particle. This was applied to the Rutherford model. So here we have the Rutherford model that we're starting with, and he used this to explain the optical spectrum for hydrogen-like atoms. Now, what is a hydrogen-like atom? Well, they're atoms with only one electron. So the first example, of course, is hydrogen. Hydrogen has one electron. Now, helium normally has two electrons, but if you take one away and make it a helium ion, it now has one electron, so it's a hydrogen-like atom. Lithium would have to be missing two electrons to only possess one electron. And then you just go up the periodic table to find other hydrogen-like atoms. He obtained good agreement with experimental data, which of course is key to any theory. Now, hydrogen, despite only having one electron, emits many wavelengths of light when it is excited. And this is what Bohr explained with his model, which was introduced in 1913. So let's start with these optical spectra and see how Bohr applied structure to Rutherford's orbiting electrons. When light is passed through a diffraction grating, and that was reviewed in an earlier chapter of this course, interference causes different colors to show up on the detection screen past the grating. Here's a picture from the electromagnetic waves unit of this course. This is xenon gas in a tube, and an electric potential is applied to either end of the tube, just like Crookes' tube. The xenon gas will emit light with frequencies that are unique to xenon, sort of a fingerprint for the element xenon. When this light is passed through a diffraction grating, it results in this spectra. No other element has this exact mix of bright lights at various different colors. This is xenon. The Rutherford model could not explain this at all. Let's start a little simpler than xenon. Here's the spectrum from ionized hydrogen gas. This is very important because it's been well studied and the equations were derived experimentally that would fit this spectra. In other words, the equations didn't come from a theory, they were just mathematically fit to the observed wavelengths and intensities and colors. That's going to be shown on the next page. What's very interesting is that these experimentally derived equations would match Bohr's theory exactly. And what we have here, here's the ultraviolet spectrum, here's infrared, and this little narrow piece is the visible spectrum. So you would see these spectra with your eye, and everything else would be out of the range of your eye. An equation that determined where the visible spectral lines from hydrogen would appear was devised back in 1885 by Johann Balmer. In 1888, Johannes Rydberg expanded the equation to include the ultraviolet and infrared lines that we saw in the previous slide from hydrogen and other hydrogen-like atoms. And again, recall that hydrogen-like atoms are atoms that only have one electron. They've lost a couple due to ionization. Note, once again, there is no theory for these lines. It's a fantastic case of matching mathematics to reality. And this is before any concept of quantum theory. The constant in these equations that made them work was later named after Rydberg, where R, the Rydberg constant, is 1.0974 times 10 to the 7th inverse meters. Here are the equations. And again, they match exactly where the hydrogen spectral lines were observed. They were named after the physicists and chemists who discovered them. So we have Balmer series, Lyman series, Paschen series, and we have 1 over the wavelength of the light equals the Rydberg constant times 1 over 2 squared minus 1 over n squared, where n in this case would be 3, 4, 5, etc., all integral values again. Or actually, for the first time, we're looking at this. And then the Lyman series would start here, and it'd go from n equals 2, 3, etc. And then the Paschen series here. Niels Bohr worked with these spectra, and in 1913 proposed that the electrons orbited the nucleus in specific energy levels. And when they absorbed energy, they would jump to a higher energy orbit. After a while, they would release this energy in the form of light and go back to their original orbit. Now, Max Planck had already come up with energy equals hf, so the energy was related to the frequency of the spectra measured. Bohr stated these orbits were quantized, so only unique light frequencies would be emitted, and that's what the spectra was showing. There were different values of intensities, there were different frequencies that showed up in the spectra. Not just any light frequency could be emitted. If that were the case, you would just have white light. It had to equal the energy difference between these orbits, and these orbits were unique to each element. So you can kind of see from this slide how the spectra could be explained.